Hi everyone, we are Team 23078 and we are proud to present our senior design project, Snorpheus. My name is Logan Dean, I'm a biomedical engineer and the team lead.
My name is Christine Carlson and I'm a biomedical engineer and the purchasing lead.
My name is Evan Brains and I'm a computer engineer.
My name is Noah Butler and I'm a computer engineer.
My name is Nisha Rajakrishna and I'm a biomedical engineer.
And we are
Team Snorpheus.
Obstructive sleep apnea, commonly known as OSA, is a sleep disorder that affects an estimated 10 to 30% of adults in the US. OSA causes repeated stopping and restarting of breathing during sleep, which can lead to decreased sleep quality and potentially extreme discomfort. Snoring and its resulting patterns can be a key indicator of OSA, but these patterns can be hard to identify in patients who don't have bed partners or who can't attend in-depth lab sleep studies. Our project aims to combat this by developing a system to accurately record and identify patient snoring, and then correlate that snoring data with body position for a full night's sleep. This informs both the patient and their clinician about what sleeping position is most likely to make patients snore, which is vital information for the development of a sleep apnea treatment plan.
The system requirements for Snorpheus are broken down into 4 categories: interface, performance, storage, and customer constraints. Now let's dive into each one of these.
The interface requirements detail specific characteristics of the system, such as a rechargeable battery, a power button, and an LED. Group 2 describes the requirements for the storage and encryption of patient data. The performance requirements detail metrics for the system's battery life, accuracy, reliability, and efficiency. The customer constraints include the system's budget, size, and usability requirements.
From the beginning, our design has been a wearable device centered around a microcontroller. It included 2 sensors, a microphone and an IMU to record audio and position data and export that data to the external processing software. Before we began construction of our project, we completed extensive testing and prototyping to ensure that our method would be effective. First, we used known audios to generate fast Fourier transforms, FFT models, and MATLAB. This ensured that we could have code that could translate audio waves into frequencies and analyze the amplitude of those frequencies.
Second, we used those FFT models to analyze the waveforms of both background noise and snoring, and we saw clear differences in the spectra. Snoring is found consistently across the frequencies of 200 to 600 Hz, with a clear peak around 215. The background noise transform peaked at various frequencies from 1 to 4K. The difference in the bands indicated to us that the FFT model would likely be effective at differentiating between background noise and snoring noises.
We then put these FFT models into graph form with spectrograms. In comparison with the background noise data, the snoring spectrogram displays clear dark blue bars with snoring audio detected. Using convolutional neural networks, which is a form of machine learning, we became confident that our software could differentiate between these 2 spectrograms. Thus, we tested to ensure that we could identify a difference between background and snoring noises.
Going in a little bit to the evolution of our prototyping and the housing for our Snorpheus system. We have laid out in front of us just some of the 3D prints that have been made in terms of testing, sizing, fitting, and going over different options for what we want Snorpheus to look like. Going from my left to my right, we have the oldest, most basic models all the way up to the newest ones that we are currently using. So our very preliminary models are just very plain boxes. They slide open and closed. The holes for the wires are the wrong size. There's just a lot wrong. Kind of going through, we've played with a couple different ideas. We did think about wrapping a microphone cord like a badge extender. And then it took a while to get the sizing right and the sliding and closure systems correct. So now our final devices look like this. We have our Raspberry Pi box with the switch and the LED in it. We have our battery box with our heat-resistant coating for the battery. And then we have the box with all other sensors and battery components such as recharging boards. And this is just some of the prototyping that's gone into the Snorpheus system.
Our extensive prototyping and testing led us to our final Snorpheus product. Here it's seen in the packaging that would be sent out to clinicians across the country. You can open it up, see a fun message to be sent to patients, and then the permanent carrier for the device is found inside the box.
This carrier box can be reused for each patient and securely stores and transports the Snorpheus recording device.
Within the device, we find the 3 unique casings that help Snorpheus performance function. First, the Raspberry Pi microcontroller right here is connected to the microphone for audio recording. Second, the IMU is housed in this casing for positional recording. Lastly, the battery is stored in this casing to fuel the device throughout the night.
Each of these pockets is hand-sewn onto the strap and secured with Velcro to ensure the data recording is consistent for a patient's full night's sleep.
Now we're going to do a demo on what it's like to put on the full Snorpheus system. So we're going to have Christine put on the Snorpheus strap. You can see the 3 boxes are going to sit at the front and center of the chest. Then in the back, it's a very simple Velcro strap that can be adjusted for multiple different sizes for different people. And that's it.
Snorpheus software breaks down into 2 systems. In the on-device portion, position and audio data is collected and encrypted. On the hub side, data is retrieved from the device, decrypted, processed using an integration of the YAMNet algorithm, and visualized for analysis. Let's see this in action. We will now take a look at the Snorpheus hub. With the proper credentials, we can gain access to the website. The Snorpheus hub is a place for clinicians to gather, analyze, and process data from their Snorpheus devices. At the bottom of the page, we have a section for fetching and processing data from a device, as well as controls for rewinding and stopping the playback of audio. Let's open up a past session. The data is immediately displayed on the 2 charts. Let's take a closer look at this section. By clicking on a snore event, we can hear its audio. Orientation of the body is represented on the y-axis from -90 to 90 degrees, as well as on the radial chart, which gives a more intuitive understanding of the body position. Let's see an example of importing device data. We will enter the device ID at the top, from 1 through 15 in this case. The patient name and last name are then entered, followed by any other information. The Snorpheus hub then attempts to connect to the given device. It retrieves the encrypted data, decrypts it, processes it, and makes it available as a session.
Lastly, we present our project poster for Snorpheus. We start by introducing obstructive sleep apnea and the medical need for our project. We then show some of the prototyping and the evolution that went into our final device, including 4 of the 3D printing iterations. We present our solution, including the hardware and 3D printed casings, as well as the software and the neural networks. Our final results include the clinician portal for data visualization, the wearable device itself, and the packaging.
Throughout the last 8 months, we have worked hard to create a product that will aid clinicians in their diagnosis of sleep apnea and lessen the negative effects of this disease. Our product, Snorpheus, helps clinicians determine what body position is most likely to make their patients snore and thus aids in the treatment of sleep apnea. We are confident that Snorpheus will help patients across the nation attain better sleep.